In the early 20th century, the understanding of atomic structure was undergoing a revolutionary transformation. Physicists were grappling with phenomena that classical physics could not explain. The atom, once thought to be indivisible and featureless, was now revealed to be a complex system of subatomic particles, each with properties that were far stranger than anything in everyday experience. Among these properties was one that would become central to the development of quantum mechanics: spin. The concept of spin, which today is recognized as an intrinsic form of angular momentum carried by particles, was unknown and unimagined before the 1920s. It was the Stern-Gerlach experiment, conducted in 1922 by Otto Stern and Walther Gerlach, that provided the first experimental evidence of this mysterious quantum property, forever changing the landscape of physics. The scientific environment of the time was one of rapid discovery and debate. Niels Bohr had proposed his model of the atom in 1913, introducing the idea that electrons orbit the nucleus in discrete energy levels. This model successfully explained the spectral lines of hydrogen, but left many questions unanswered, particularly regarding the finer details of atomic spectra and the magnetic behavior of atoms. Classical theories of magnetism could not account for certain experimental results, and a new framework was required. Stern and Gerlach were motivated by one such puzzle: the behavior of silver atoms in a magnetic field. Otto Stern, trained as a physicist in Germany, had a deep interest in molecular beams and the measurement of atomic properties. Walther Gerlach, a skilled experimentalist, collaborated with Stern to design an experiment that could test the quantization of angular momentum, a concept proposed in the context of the old quantum theory but still unverified. The fundamental question they sought to answer was deceptively simple. When a particle with angular momentum is exposed to a non-uniform magnetic field, how does it respond? Classical physics predicted a continuous distribution, much like a compass needle that can point in any direction depending on the magnetic influence. But the nascent quantum theory suggested that only discrete orientations should exist. Testing this idea required ingenuity, precision, and a deep understanding of both theory and experimental technique. The setup of the Stern-Gerlach experiment was elegant in its simplicity, but demanding in its execution. A beam of silver atoms was generated by heating silver in an oven until it vaporized, producing a stream of atoms moving at high speed. These atoms were then collimated through a series of narrow slits to produce a thin, directed beam. The beam was directed into a region with a non-uniform magnetic field, carefully designed so that the gradient of the magnetic field would exert a force on the magnetic moment of the atoms. At the end of the apparatus was a detector screen coated with a substance that would reveal where the atoms struck. According to classical expectations, the atoms would spread out in a continuous pattern along the axis of the magnetic field gradient, reflecting the full range of possible orientations of the magnetic moments. What Stern and Gerlach observed was astonishing. Instead of a continuous smear, the silver atoms split into two distinct spots on the detector screen. This discrete separation indicated that the magnetic moment of each silver atom could only take one of two possible orientations relative to the magnetic field. The implication was profound. The angular momentum associated with the atoms was quantized, existing in only specific, discrete states. This quantization could not be explained by classical mechanics. The result provided the first direct experimental evidence of a quantum property that would later be called spin. It is important to understand why the experiment revealed spin, even though the term spin was not used at the time. The silver atom has a single electron in its outermost shell, and the magnetic properties measured in the experiment are primarily due to this electron. The splitting of the beam into two distinct lines corresponded to two possible spin states of the electron, which were later identified as spin up and spin down. This discovery confirmed the theoretical notion that electrons possess an intrinsic form of angular momentum that is not due to literal spinning in space, but is a fundamental property of the particle itself. The Stern-Gerlach experiment, therefore, provided a window into the hidden world of quantum mechanics, where particles behave according to rules that defy classical intuition. The impact of this experimental breakthrough was immediate and far-reaching. For the first time, physicists had tangible evidence that nature at the atomic scale is inherently discrete and quantized, not continuous. The concept of spin introduced a new degree of freedom for particles, influencing not only atomic structure but also chemical bonding, magnetism, and the statistical behavior of matter. The discovery forced theorists to revise their models and laid the groundwork for the formulation of quantum mechanics in the following decades. Wolfgang Pauli would introduce the exclusion principle in 1925, directly connecting spin to the arrangement of electrons in atoms. Later, spin would become essential in understanding phenomena ranging from the fine structure of spectral lines to the behavior of elementary particles in quantum field theory. The elegance of the Stern-Gerlach experiment lies not only in its scientific significance, but also in its methodological brilliance. At a time when quantum mechanics was still in its infancy, Stern and Gerlach demonstrated that careful experimental design could reveal the hidden rules of the microscopic world. The apparatus was simple enough to avoid unnecessary complications, yet precise enough to detect a subtle effect that had eluded observation. This combination of simplicity and precision is a hallmark of great experimental physics, and a reason why the experiment continues to be celebrated almost a century later. Beyond its technical achievements, the experiment also reshaped philosophical thinking about the nature of reality. The discrete outcomes observed in the Stern-Gerlach experiment hinted at a world where determinism gives way to probability, where observation and measurement play a fundamental role in shaping physical outcomes. This challenged deeply held notions inherited from classical physics and set the stage for debates that continue to this day about the interpretation of quantum mechanics. In revealing spin, Stern and Gerlach not only uncovered a new property of matter, but also opened the door to a deeper understanding of how the universe operates at its most fundamental level. The historical significance of the Stern-Gerlach experiment cannot be overstated. It was a turning point in physics, bridging the gap between abstract quantum theory and observable reality. It demonstrated that careful experimentation could confirm theoretical predictions that seemed almost mystical at the time. By revealing spin, Stern and Gerlach provided a concrete foundation for future discoveries, from the development of quantum statistics to the manipulation of spin in modern technologies like magnetic resonance imaging and quantum computing. Their work exemplifies the power of curiosity, rigorous methodology, and bold inquiry, qualities that define scientific progress. Finally, the story of the Stern-Gerlach experiment is a testament to the importance of asking the right question. Stern and Gerlach did not set out to discover spin specifically. They sought to test a prediction of quantized angular momentum. Yet their careful approach, combined with innovative experimental design, led to a discovery that would resonate across physics for generations. The revelation of spin was not just a technical achievement. It was a conceptual revolution, reshaping our understanding of the microscopic world and laying the groundwork for the quantum technologies that now define modern science. As the scientific community absorbed the results of the Stern-Gerlach experiment, the implications began to spread far beyond the original goal of measuring quantized angular momentum. What had first appeared as an unexpected splitting of silver atoms soon became the key to understanding an entirely new quantum property. Spin, once revealed, demanded a deeper theoretical explanation. Physicists realized that this newly uncovered feature was unlike any classical phenomenon. It did not correspond to a tiny particle physically rotating like a miniature planet, nor could it be described by traditional mechanical motion. Instead, it represented a fundamentally quantum characteristic, embedded directly in the nature of matter itself. The early theoretical attempts to explain the behavior observed in the experiment faced significant challenges. Classical physics had no concept of intrinsic angular momentum. If the electron were literally spinning, calculations showed it would require an impossible rotation speed faster than light to produce the observed magnetic moment. This contradiction made it clear that spin was not a classical rotation. It had to be treated as a purely quantum property. Physicists such as Wolfgang Pauli began exploring this strange new feature, ultimately concluding that each electron possessed an internal degree of freedom that could take on exactly two possible values. These two values corresponded directly to the two discrete spots created in the Stern-Gerlach apparatus. Pauli's work was pivotal. He introduced what would later be called the Pauli exclusion principle, stating that no two electrons in an atom can have the same set of quantum numbers. This principle explained why electrons fill atomic shells in the specific patterns observed by chemists. Without spin, the structure of the periodic table would remain a mystery. The stability of matter, the shapes of molecules, and the rules of chemical bonding all hinged on this internal two-state system that the Stern-Gerlach experiment had revealed. What began as a demonstration of magnetic quantization evolved into a cornerstone of modern chemistry. The growing evidence pushed physicists to expand the mathematical framework of quantum mechanics. When Schrödinger introduced his wave equation in 1926, it provided a powerful tool for describing the behavior of electrons. Yet it did not include spin. The equation could describe the orbital motion of electrons around the nucleus, but it could not explain the extra quantum number required by the Stern-Gerlach results. The real breakthrough came when Paul Dirac, working to unify quantum mechanics with special relativity, formulated an equation that naturally predicted the existence of spin as an intrinsic property of electrons. Even more astonishingly, the equation also predicted the existence of antimatter. This mathematical development solidified spin as a fundamental aspect of reality, not merely an experimental anomaly. The understanding of spin deepened further when scientists recognized that it plays a central role in the magnetic properties of materials. Ferromagnetism, the phenomenon that allows certain materials to become permanent magnets, arises from the alignment of electron spins within atoms. Without the Stern-Gerlach experiment, this underlying mechanism might have remained hidden much longer. The experiment also helped clarify why some materials become strongly magnetic, while others remain non-magnetic. It all depends on how the spins of electrons pair or align. These insights provided the foundation for countless applications, from electric motors to data storage devices. Another essential development inspired by the Stern-Gerlach findings was the concept of spin measurement itself. The experiment revealed that when a particle with spin enters a magnetic field, it must choose one of the allowed orientations. This choice, is not made before measurement. Instead, it is fundamentally probabilistic. The outcome becomes definite only when the particle interacts with the measuring apparatus. This observation cut directly into the heart of the debate over the nature of quantum reality. It raised profound questions. Does the act of measurement create the outcome? Are the physical properties of quantum particles undefined until measured? The Stern-Gerlach experiment thus became an early example of how measurement interacts with quantum systems, foreshadowing discussions about wave, function collapse, superposition, and the role of observation in quantum theory. Years later, variations of the experiment continued to shed light on the quantum world. By using different atoms or adding additional magnetic stages, scientists discovered that spin behaves according to specific mathematical rules known as spin operators. These operators do not follow the same algebra as classical vectors. Instead, they require a special type of matrix mathematics introduced by Werner Heisenberg. This mathematical structure is now fundamental in quantum mechanics, showing how spin transforms, interacts, and evolves over time. The Stern-Gerlach experiment, therefore, did more than detect spin. It motivated the mathematical tools needed to describe it. One of the most surprising aspects of spin is its connection to quantum superposition. In the original experiment, the two-spot pattern indicated that the silver atoms arrived either in one state or the other. But before measurement, a quantum particle can exist in a combination of both spin states at once. This is not a physical mixture, but a genuine superposition, a concept that has no counterpart in classical physics. Modern experiments, derived from the Stern-Gerlach design, can prepare particles in specific superpositions and track how they evolve. These ideas are now central to quantum computing. The basic unit of quantum information, the qubit, is directly based on the idea that a particle's spin can represent both up and down. Simultaneously, spin also plays a role in one of the most fascinating phenomena in quantum physics, entanglement. When two particles interact, their spins can become correlated in ways that remain connected even when the particles are separated by large distances. Measuring the spin of one immediately determines the spin of the other, regardless of how far apart they are. This non-local behavior, which Einstein famously called spooky action at a distance, is now well established and forms the foundation of quantum communication and quantum encryption technologies. The Stern-Gerlach experiment was the doorway to this understanding, revealing spin as a quantum property capable of participating in these remarkable correlations. The influence of spin extends to the world of modern medical and imaging technologies. Magnetic resonance imaging, or MRI, works by manipulating the spins of hydrogen nuclei inside the human body. When these nuclear spins are aligned and then disturbed by radio frequency pulses, they emit signals that can be measured and converted into detailed images of soft tissue. The precision and safety of MRI have made it one of the most important medical tools of the modern era. Its existence depends entirely on the fact that particles have intrinsic spin knowledge made possible by the original Stern-Gerlach experiment. Another emerging field shaped by spin is spintronics. Unlike traditional electronics, which rely on the electrical charge of electrons, spintronics uses the spin of electrons to encode and process information. Devices based on spin can potentially be faster, more efficient, and more compact than conventional electronics. From ultra-dense data to storage to new forms of logic circuits, Spintronics is pushing the boundaries of what technology can achieve. Once again, the journey traces back to the recognition of spin as a measurable and controllable quantum property. As the decades passed, the experiment itself evolved into a key demonstration in quantum education. In classrooms and laboratories, simplified versions of the Stern-Gerlach apparatus help students visualize the abstract nature of quantum mechanics. It serves as a concrete example of how quantum measurements produce discrete outcomes, how superposition collapses into definite states, and how quantum properties differ fundamentally from classical behaviors. The experiment has become a teaching tool for illustrating the difference between the everyday world and the quantum realm. Despite its age, the experiment continues to inspire new research. Modern scientists use advanced versions to explore quantum coherence, decoherence, and the transition between quantum and classical behavior. By adjusting the experimental conditions, researchers can study how spin states lose coherence through interaction with the environment. This research is crucial for developing stable quantum computers and for understanding where the boundary lies between quantum behavior and classical experience. The full story of the Stern-Gerlach experiment reveals why it stands as one of the most important discoveries in the history of physics. It did not merely uncover a new property of particles, it reshaped the theoretical landscape, influenced the development of technologies that permeate modern life, and illuminated the philosophical foundations of quantum theory. The experiment showed that nature is built from discrete quantum choices rather than continuous classical possibilities. It demonstrated that measurement plays an active role in determining physical outcomes, and it opened the door to new fields of research that continue to expand our understanding of the universe. The discovery of spin was much more than a technical observation. It was a conceptual breakthrough. It forced scientists to rethink how they described the microscopic world. It revealed that particles carry hidden qualities accessible only through precise and carefully designed experiments. And it provided a lasting foundation for nearly every major advancement in modern physics, from atomic theory to quantum field theory. For centuries, classical physics had shaped the way scientists understood the behavior of matter. The principles laid down by Newton, Maxwell, and others painted a picture of a universe governed by continuity, smooth trajectories, gradual changes, and predictable outcomes. Every object, from a falling apple to a spinning planet, followed laws that allowed future behavior to be calculated with precision. Even when scientists began exploring atoms, many assumed these same rules would apply on the microscopic scale. They imagined electrons moving like tiny planets around a nucleus, possessing any orientation or energy within a continuous range. The world, both big and small, appeared to operate under the same seamless, deterministic principles. This viewpoint remained dominant well into the early 20th century. Classical physics had been spectacularly successful in describing mechanical motion, electromagnetic waves, heat, and much else. So when physicists encountered puzzling phenomena at the atomic level, many believed these problems would eventually be solved by refining existing theories. The idea that atoms might not obey classical continuity felt radical, almost unacceptable. Yet these classical assumptions were built on observations of macroscopic objects, things large enough to follow predictable paths. No one had directly observed the behavior of individual atoms or electrons. The atomic world was a mystery waiting to be uncovered. The Stern-Gerlach experiment became one of the first decisive cracks in the classical world view. When Otto Stern and Walther Gerlach designed their experiment, they intended to test whether atomic angular momentum was continuous or quantized. According to classical physics, an atom with magnetic properties should be able to orient itself in infinitely many angles when placed in a magnetic field. Just as a spinning top can lean at any angle, an atom's magnetic moment should respond smoothly and continuously. If this were true, the silver atom beam in their experiment would spread out into a continuous smear on the detector screen, forming a gradual distribution without gaps. But quantum theory, still in its early formation, suggested something very different. If atomic angular momentum were quantized, then atoms should only adopt specific orientations, discrete, separated values. Instead of a smear, the beam would break into distinct spots. Many physicists at the time found this idea difficult to accept. Quantization seemed too rigid, too unnatural compared to the fluid behavior seen in classical systems. Yet the Stern-Gerlach apparatus provided the perfect stage to reveal which view was correct. When the experiment was performed in 1922, the results were astonishing. Instead of a continuous distribution, the silver atoms split into exactly two distinct beams. This was not a small deviation from classical expectations. It was a complete rejection of them. The atoms behaved as though they were forced to choose one of two allowed orientations, with nothing allowed in between. The detector showed two sharp spots, separated by a clear gap where no atoms appeared. The classical prediction of continuous outcomes failed utterly. This splitting demonstrated, for the first time in a direct, visual way, that atoms do not behave according to classical continuity. Their magnetic properties, and by extension their angular momentum, come in discrete units, fixed, quantized states. Nature at the atomic scale is built from steps, not smooth lines. The Stern-Gerlach experiment thus challenged one of the deepest assumptions of classical physics, that physical properties vary continuously and can take any value within a range. The implications of this discovery were profound. Classical physics assumed determinism. If you know the initial conditions, you can predict the future exactly. But quantization introduces fundamental limits on what a particle can do. It cannot adopt every possible orientation. It must occupy one of a small set of specific states. This meant that at the atomic level, the universe works by rules fundamentally different from the macroscopic world. The experiment provided clear evidence that quantum mechanics was not merely a mathematical convenience, but a real feature of nature. What made this discovery even more striking was its simplicity. The apparatus consisted only of a heated oven, slits, a magnetic field, and a detector screen. No advanced electronics, no complex machinery, just pure physics. Yet this simple setup produced a result that classical theory could not explain. The sharp splitting observed on the detector forced scientists to confront the limitations of their long-held assumptions. If angular momentum was quantized, then many other atomic properties might be as well. This realization opened the door to a new scientific revolution. The unexpected results also raised philosophical questions that challenged classical thinking. If atomic properties are quantized, then the universe is not fully continuous. But even more troubling was the idea that atoms do not choose a specific state until they interact with a measuring device. Before entering the Stern-Gerlach apparatus, a silver atom does not have a definite orientation of its magnetic moment. It exists in a superposition, a mixture of possible states. Only when it passes through the magnetic field does it decide whether to go up or down. This challenged the classical concept of realism, the belief that physical properties exist independently of measurement. These insights pushed physicists to rethink the foundations of their theories. If atoms behave discretely rather than continuously, then the mathematical tools used to describe them must reflect this. Classical differential equations, which model smooth, continuous change, were no longer sufficient. New mathematical frameworks, such as operators, matrices, and wave functions, were required to capture the quantized, probabilistic nature of atomic behavior. The Stern-Gerlach experiment thus played a critical role in driving the development of quantum mechanics, forcing theorists to abandon classical assumptions and adopt new principles. One of the most revolutionary aspects of the experiment was its implications for angular momentum. In classical physics, a spinning object can rotate with any value of angular momentum depending on how much force is applied. But the experiment showed that atomic angular momentum comes in discrete units, and these units depend on fundamental quantum numbers. This was not merely a minor correction. It redefined the understanding of rotational behavior at the microscopic level. The experiment demonstrated that at the quantum scale, the universe is governed by symmetry rules and mathematical constraints that have no parallel in classical physics. The discovery also reshaped how scientists viewed magnetism. Classical theories treated magnetism as a property that arises from the motion of charged particles. But the Stern-Gerlach results showed that magnetism has a deeper quantum foundation tied to intrinsic particle properties. Electron spin, which was uncovered indirectly through the experiment, became the key to understanding magnetic materials, atomic structure, and chemical behavior. The classical view that magnetism was simply due to orbital motion of electrons around the nucleus was incomplete. Instead, magnetism arises from both orbital and intrinsic angular momentum, something classical physics could never have predicted. As the consequences of the experiment spread, scientists began to explore other classical ideas that might fail under quantum scrutiny. The notion that particles have definite positions and velocities at all times was increasingly questioned. The smoothness and predictability of classical trajectories gave way to the probabilistic nature of quantum waves. Instead of describing particles as tiny spheres following precise paths, quantum mechanics describes them as wave functions that spread, interfere, and collapse during measurement. The Stern-Gerlach experiment played a major role in this conceptual shift, showing that physical outcomes emerge through discrete interactions rather than continuous evolution. The challenge to classical continuity became even more significant when scientists considered the idea of measurement itself. In classical physics, measurement is passive. It reveals a property that already exists. But in the quantum world revealed by the Stern-Gerlach experiment, measurement is active. It forces a system into one of several possible states. Before measurement, the atom's magnetic orientation is not a single, definite value. The experiment compelled scientists to rethink the nature of reality at the smallest scales. Does a quantum system have properties before we measure them? Or is measurement part of what defines these properties? The results of the Stern-Gerlach experiment suggested that classical realism, the idea of pre-existing definite states, may not hold in the quantum domain. Moreover, the experiment spurred deeper investigations into the mathematical structure of angular momentum in quantum mechanics. Physicists discovered that the allowed values of angular momentum are determined by quantum numbers and follow specific algebraic rules. The possible orientations of angular momentum are quantized based on these numbers, not on classical angles. This formed the foundation for spin matrices, the concept of spin operators, and the understanding of how angular momentum behaves under rotations. None of these mathematical ideas existed in classical physics, and all were inspired by the experimental evidence revealed by the Stern-Gerlach setup. The experiment also played a crucial role in the development of modern atomic theory. Classical models struggled to explain the fine structure of spectral lines, the small splittings and shifts observed in atomic emission spectra. The quantization of angular momentum revealed by the experiment provided the missing piece of the puzzle. It helped physicists understand why atomic spectra have their intricate structure, and how electron spin interacts with orbital motion to produce these patterns. Classical physics could not account for these features, but quantum mechanics, informed by the Stern-Gerlach results, explained them beautifully. Even more fundamentally, the experiment challenged the idea of classical determinism. Classical physics assumes that if you know the current state of a system precisely, you can predict its future state exactly. But the Stern-Gerlach experiment showed that even with complete knowledge of an atom's motion before entering the magnetic field, you cannot predict which orientation it will choose. The outcomes are probabilistic, not deterministic. This marked a dramatic shift away from the classical world, contributing to the development of the probabilistic interpretation of quantum mechanics championed by Born, Heisenberg, and others. The experiment also influenced broader philosophical discussions. If atomic properties appear only when measured, then observation plays a central role in shaping physical reality. This idea contrasted sharply with classical objectivity, where the universe evolves independently of observers. The Stern-Gerlach experiment became one of the earliest examples of how quantum systems require observers, not because consciousness alters physics, but because measurement defines the state of system. This realization prompted decades of debate about the meaning of quantum mechanics, leading to interpretations such as the Copenhagen interpretation, many worlds theory, and decoherence models. The challenge to classical continuity was not theoretical alone. It became embedded in practical technologies. Devices based on magnetic fields, quantum states, and spin behavior now rely on principles that originated from the breakdown of classical assumptions. Technologies such as MRI machines, nuclear magnetic resonance devices, spintronic components, and quantum computers owe their operation to the discrete, quantized nature of atomic properties. These technologies demonstrate that the quantum rules revealed by the Stern-Gerlach experiment are not abstract curiosities, they are the operational foundation of modern physics and engineering. Ultimately, the experiment forced scientists to accept that the microscopic world obeys a different set of rules. Classical continuity, once considered universal, was replaced by quantum discreteness. Atoms do not rotate in smooth arcs, they jump between defined states. Electrons do not possess unlimited orientations, they adopt quantized ones. Measurement does not reveal pre-existing values, it constructs outcomes from probabilistic possibilities. The Stern-Gerlach experiment was one of the earliest and most convincing demonstrations of these truths. Its results stand as a reminder that intuition built from everyday experience cannot always explain the behavior of nature at its smallest scales. The atomic world is not simply a scaled-down version of the macroscopic world. It is fundamentally different. The experiment revealed that continuity, predictability, and determinism fail where quantization, probability, and measurement dominate. By challenging classical views at their core, the Stern-Gerlach experiment helped usher in the quantum revolution, forever changing the understanding of matter, motion, and reality itself. The deeper you dive into the Stern-Gerlach experiment, the more you begin to realize that its true power lies not in the metallic oven, or the vacuum chamber, or the silver atoms flying through a magnetic field, but in the astonishing idea that a physical quantity we once imagined as smooth and continuous is instead quantized, locked into discrete categories that nature refuses to blur, no matter how elegantly classical physics tries to demand otherwise. Classical physics predicted a gentle smear of results, a smooth distribution of deflections, a picture consistent with the idea that a spinning object, no matter how tiny, should point in any direction allowed by geometry. Yet when the experiment ran, that expected smear decayed into two sharp spots. Not a continuum, not a gradient, just two places, like nature ticked one box or the other. This is where the importance of the second keynote, the collapse of classical intuition, becomes painfully and beautifully clear. To understand why this matters so much, imagine trying to solve a puzzle where every piece looks curved, flowing, and flexible, but the solution requires snapping rigid blocks into place. Physics before 1922 believed in curves, smooth orbits, smooth rotations, smooth energies. The entire world, was built on continuity. So when Stern and Gerlach saw discreteness instead, the shock wasn't just an experimental surprise. It was a conceptual earthquake. Even the world's smartest physicists did not expect matter to behave like this. The theory of quantized angular momentum was still young and controversial, and quantum mechanics as a complete framework didn't even exist yet. Bohr had suggested quantized orbits, but those were tied to specific atomic energy levels. No one expected space itself to impose discrete orientations on the tiniest magnets. The experiment exposed a truth that theory hadn't fully caught up with. The quantum world is not just about energy levels, but also about fundamental properties like orientation and angular momentum. Nature was being far more radical than classical physicists had allowed themselves to imagine. But to appreciate the full weight of this discovery, consider how the result challenges even the most intuitive classical analogies. Think of a spinning top. You can tilt it slightly, or a lot, or anywhere in between. There's no rule that says it must point up or down only. It obeys geometry, not categories. But Stern-Gerlach showed that for atomics, Gale tops, nature enforces categories. The magnetic moment of the silver atom cannot tilt into random angles when measured. It is forced into specific quantum, defined orientations. It is as if every tiny top in the universe has to choose from a tiny menu of allowed angles, and these options depend not on the environment or the setup, but on the built-in quantum structure of matter itself. This is the moment when classical physics quietly steps aside, realizing that it can no longer describe the world with continuous assumptions. You can't force discreteness into a classical picture without stretching it beyond recognition. What makes this transition even more profound is that the Stern-Gerlach experiment didn't just confirm what early theorists were guessing. It revealed something that theory had not yet fully articulated: the existence of electron spin. At the time, scientists didn't yet know that the electron carried a fundamental truth, angular momentum, spin. The experiment delivered the evidence before the full explanation existed. It was like receiving a message before knowing the language it was written in. Later, when Uhlenbeck and Gaudsmit introduced the idea of electron spin, the strange bot pattern suddenly made perfect sense. But Stern and Gerlach had unknowingly revealed this structure before the concept was even invented. The experiment was not just a verification tool, it was a discovery engine. It produced data that forced theorists to rethink the basic identity of the electron itself. This is where the collapse of classical intuition becomes more than a shift in mathematics. It becomes a shift in world view. Classical physics encourages us to imagine atoms as small, structured objects behaving like miniature planets or tops. But the quantum picture that emerges from this experiment tells us that atoms don't fit into those analogies at all. They don't rotate like tiny spheres with smooth angular momentum. They possess quantized, intrinsic, indivisible angular momentum that isn't derived from physical spinning at all. The Stern-Gerlach experiment exposed the limits of metaphor. It told the scientific world that the universe is not obligated to follow human-shaped intuitions. It behaves according to structures that don't map neatly onto our everyday experiences. And even more interesting is the idea that the experiment forced physicists to reconsider the role of measurement itself. The silver atoms entered the apparatus with no specified orientation. They were a cloud of uncertainty, a distribution of possible angular momentum states. But the moment they passed through the magnetic field, the measurement forced the system to pick an allowed state. This wasn't just detecting information, it was transforming the system. Measurement became active, not passive. This realization set the foundation for the modern understanding of quantum measurement, wave-function collapse, and the idea that observing a quantum system changes it. The Stern-Gerlach experiment didn't just break classical intuition. It replaced it with a new idea that would become one of the most debated and misunderstood concepts in quantum mechanics. Another layer of significance comes from how the experiment hinted at the geometry of quantum states. The two spots represent the simplest quantum system imaginable, a two-level system. Today, we call this a qubit, the building block of quantum computing. Every qubit in a quantum computer, every superposition, every entangled pair has a history that traces back to that unexpected pattern of two spots on a screen in 1922. Without Stern-Gerlach, the existence of discrete spin states might have taken longer to validate, delaying the development of particle physics, quantum information theory, and even the technologies built on spin, such as MRI machines and spin-based transistors. The experiment was not just important for theory, it laid the foundation for real-world applications that now touch everyday life. The collapse of classical intuition also reshaped how physicists interpret the nature of space itself. In classical thinking, space provides a backdrop objects can rotate in it freely and continuously. But the Stern-Gerlach experiment showed that space at quantum scales operates under internal constraints. Angular momentum can't just point anywhere. It must align with quantized axes defined by the measurement interaction. This discovery hinted at the mathematical structure of quantum state space, a space of possibilities that doesn't resemble physical space at all. Instead of coordinates and directions, it is defined by probability amplitudes, operators, and eigenstates. The scattering pattern on the plate was like the first shadow cast from this higher, dimensional quantum reality onto the classical world. In a broader sense, the experiment signaled a turning point in how physicists think about cause and effect. Classical causality expects that if you know all initial conditions, positions, velocities, orientations, you should be able to predict all future outcomes precisely. But the Stern-Gerlach experiment made it clear that knowing everything about a quantum particle still doesn't allow classical prediction. You can predict probabilities, not exact results. This wasn't an accidental limitation, it was fundamental. It represented a new rulebook for the microscopic universe, one that classical physics simply wasn't built to handle. The beauty of this transition is that Stern-Gerlach didn't provide a complicated dataset. It provided a simple picture, two spots. Yet those two spots carried a message that rewrote physics. They said that the universe is quantized. They said that nature restricts how particles can orient themselves. They said that measurement forces a choice among discrete states. They said that classical analogies fail at small scales. And most importantly, they said that the deepest truths of nature can emerge from the simplest experiments, if we are willing to see them. When the Stern-Gerlach experiment was conducted in 1922, physics was standing at a crossroads. Classical theory had already begun to fracture under the weight of new discoveries about atoms and energy, yet quantum theory was still in its infancy. More guesswork than structure, more intuition than clarity. The experiment played a decisive role in shifting quantum physics from an intriguing idea to a solid, evidence-based framework. It did this not by producing complicated data, but by delivering a result so clear, so impossible to reconcile with classical physics, and so aligned with early quantum ideas that it became one of the strongest experimental pillars supporting the construction of quantum mechanics. At the time, quantum theory was mostly mathematical speculation. Max Planck had introduced quantized energy to explain blackbody radiation. Bohr had used quantized orbits to describe the hydrogen atom. However, both ideas were controversial. Many physicists were uncomfortable with the idea that nature would enforce strict jumps, or fixed values instead of the smooth, continuous behavior expected from classical mechanics. There was no direct experimental demonstration that quantization affected the very orientation of physical systems. That is where the Stern-Gerlach experiment provided the missing piece. It showed that even the direction of angular momentum, something tied to the geometry of space itself, was quantized. This was a revolutionary step. When a beam of silver atoms passed through the non-uniform magnetic field, classical physics predicted a continuous spread of positions on the detection plate. Slight differences in the magnetic orientation of each atom should have produced a smooth pattern, but instead, the atoms formed two sharp, separate clusters. That simple image, two clean spots rather than a blurred smear, was undeniable evidence that some property of the atom existed only in discrete states. This confirmed a central prediction of early quantum theory, that certain physical quantities can take only specific, quantized values, not any value in a continuum. In one stroke, the experiment provided direct visual proof that the quantum world view was correct. Even more importantly, the experiment offered evidence for something that theory had not yet clearly defined: intrinsic angular momentum, or spin. Though the concept of electron spin had not been formally introduced, the experiment's results hinted strongly at a two-valued quantum degree of freedom. It was as if each silver atom carried an internal, binary orientation that determined how it behaved in a magnetic field. This discovery later became crucial to the development of quantum mechanics, because spin turned out to be a fundamental quantum property with no classical analog. Without understanding spin, one cannot understand the structure of atoms, the behavior of electrons in solids, or even the periodic table. The experimental signature of spin came first, and the theoretical explanation followed. In this way, the Stern-Gerlach experiment did not merely support quantum theory, it guided its evolution. Another important contribution was the experiment's demonstration of how measurement affects quantum systems. Before the experiment, measurement in physics was thought to be passive. It revealed something that was already there. But Stern-Gerlach showed that measuring the orientation of angular momentum forced the atom to adopt one of the discrete allowed values. This result hinted at what would later become the measurement postulate of quantum mechanics, that the act of measurement collapses the quantum state. It provided a real, physical example of how quantum systems behave differently when observed. Future giants like Heisenberg and Schrödinger built this insight into the mathematical structure of quantum mechanics. Without Stern-Gerlach, his clear experimental behavior, the idea might have remained abstract for much longer. The experiment also indirectly provided support for the development of matrix mechanics, one of the earliest forms of quantum mechanics. Werner Heisenberg, Max Born, and Pascual Jordan formulated matrix mechanics in 1925, describing physical quantities like position and momentum as operators with discrete eigenvalues. The quantized results of the Stern-Gerlach experiment fit perfectly into this framework. The two allowed outcomes corresponded to eigenvalues of an angular momentum operator. Though this connection was recognized later, the experiment gave theorists confidence that nature truly followed quantized rules, which strengthened the philosophical foundations of matrix mechanics and helped physicists accept its radical departure from classical ideas. In addition, Stern-Gerlach helped validate Pauli's exclusion principle and the concept of electron-spin pairing. Wolfgang Pauli introduced the exclusion principle in 1925 to explain atomic structure and electron arrangements. However, the idea required that electrons possess an internal two-valued degree of freedom, something not yet fully established. When Uhlenbeck and Gaudsmit proposed the concept of electron spin later that year, the Stern-Gerlach experiment suddenly became the perfect historical evidence supporting this idea. The experiment showed that particles naturally come in two spin states, a feature essential for explaining why electrons fill atomic orbitals the way they do. The structure of the periodic table, the stability of atoms, and the behavior of matter all depend on this. In this way, Stern-Gerlach became a central piece of the puzzle allowing quantum theory to evolve into a coherent, predictive model of atomic physics. The experiment also influenced the development of quantum field theory and particle physics. Spin, the property revealed experimentally, became one of the defining characteristics of elementary particles. Modern theories classify particles by their spin values. Fermions have half-integer spin, and bosons have integer spin. This classification underlies the structure of matter and forces in the universe. None of this could have been built with confidence without experimental proof that spin existed. Stern-Gerlach provided that proof long before theorists fully understood its implications. Beyond theoretical advances, the experiment built trust in quantum theory. Early quantum ideas were strange and counterintuitive, and many physicists resisted them. But the undeniable clarity of the Stern-Gerlach result convinced even skeptics that the quantum world operated differently from the classical world. It showed that quantization was not just a mathematical trick, but a feature deeply embedded in nature. This confidence helped accelerate the acceptance of new theories emerging in the 1920s and early 1930s. Most importantly, the experiment demonstrated the power of simple, well-designed experiments in shaping theoretical revolutions. With just a beam of atoms, a magnetic field, and a detection plate, Stern and Gerlach produced a result that reshaped physics. It gave quantum theory the solid ground it needed to grow into a complete framework. It proved that quantized properties exist even in the simplest atomic systems. It hinted at spin, guided theoretical developments, supported the conceptual foundation of measurement, and helped physicists transition from classical intuition to quantum understanding. Because of these contributions, the Stern-Gerlach experiment is not just an example of experimental success. It is one of the major pillars that made quantum mechanics possible. Without it, quantum theory might have evolved much more slowly, less confidently, and with far more theoretical uncertainty. Its legacy is not only historical but foundational, continuing to influence our understanding of atoms, particles, information, and the structure of the universe. When the Stern-Gerlach experiment was performed in 1922, no one imagined that its strange two-spot pattern would eventually lead to some of the most powerful technologies of the modern era. Yet the experiment uncovered a fundamental property of matter, spin, that now sits at the heart of technologies ranging from medical imaging to quantum computers. What Stern and Gerlach observed was not just a physics curiosity. It was the first glimpse into the behavior of quantum spins, a property that would later become a driving force behind scientific, medical, and technological breakthroughs. The key contribution of the experiment was establishing that particles possess quantized spin states. Before the experiment, there was no clear evidence that microscopic particles had an intrinsic angular momentum that could take only specific values. When the silver atoms split into two beams instead of forming a continuous pattern, it revealed that their magnetic moments, and therefore their spins, could occupy only discrete states. This insight became one of the foundational principles of quantum mechanics. But beyond reshaping theory, it created the physical basis for technologies that rely on precise control and detection of spin. One of the clearest examples of this technological impact is magnetic resonance imaging, or MRI. MRI is built entirely on the concept of nuclear spin, the same kind of quantized magnetic orientation discovered indirectly by Stern and Gerlach. In MRI machines, the spins of hydrogen nuclei in the body respond to strong magnetic fields. These spins can align in different directions, just like the atoms in the Stern-Gerlach experiment. By manipulating these spins with radio frequency pulses and detecting how they release energy when they return to their original states, MRI scanners create highly detailed images of tissues and organs. Without the discovery that spins come in discrete, measurable states, MRI technology would quite literally not exist. The Stern-Gerlach experiment laid the conceptual groundwork by proving that spins are real, quantized, and responsive to magnetic fields. Furthermore, MRI relies on an idea directly connected to the experiment, that spins precess and change alignment under magnetic influence. The experiment showed that atoms are deflected based on their magnetic orientation. Modern MRI takes this principle much further by controlling spins with extraordinary precision. Every time someone undergoes an MRI scan, millions of atomic spins inside their body are aligning, flipping, and relaxing in ways that echo the core results of the 1922 experiment. What began as a curious splitting of a silver atom beam turned into a medical imaging tool that saves lives by detecting tumors, mapping brain activity, and revealing internal injuries without harmful radiation. But the influence of Stern-Gerlach extends even further into the frontier of technology: quantum computing. Quantum computers depend on quantum bits, or qubits, which are fundamentally different from classical bits. While classical bits can only be 0 or 1, qubits can exist in superpositions of both states at once. The earliest example of a physical qubit comes from spin-of particles, the exact kind revealed in the Stern-Gerlach experiment. A qubit can be represented by a spin pointing up, down, or in a quantum superposition of up and down. In other words, the two allowed spin states observed in the experiment form the blueprint for how qubits behave. The splitting into two discrete beams in the Stern-Gerlach setup is essentially the first demonstration of a two-state quantum system, the most important ingredient of quantum computing. Modern qubit systems, whether based on trapped ions, superconducting circuits, semiconductor spins, or nitrogen, vacancy centers in diamonds, use the same principle. There are two quantized energy, or spin states that serve as the computational basis. Without the knowledge that such discrete states exist and can be manipulated by magnetic or electric fields, it would be impossible to design quantum algorithms, quantum gates, and quantum circuits. The experiment also contributed indirectly to the understanding of quantum measurement, which is crucial in quantum computing. In Stern-Gerlach, atoms existed in a superposition of spin states until they were measured by the magnetic field, which forced them into one of the two possible outcomes. This is the same idea used in reading a qubit at the end of a quantum program. The computer manipulates qubits in superposition, but when the final measurement occurs, the system collapses to a classical outcome. The experiment provided one of the earliest real-world examples of such collapse, long before quantum computers were even imagined. Another major technological field influenced by Stern-Gerlach is spintronics. Traditional electronics relies on the charge of electrons, but spintronics uses their spin. Devices like magnetic memory, spin transistors, and next-generation data storage technologies are possible because spins can be aligned, flipped, and detected. The ability to split particles by spin in the Stern-Gerlach experiment showed that spin is not just a mathematical abstraction, but a physically measurable property. This opened the door to engineering spin-based devices that could operate faster, consume less power, and store more information than classical electronics. Even atomic clocks, some of the most precise instruments ever built, owe part of their development to the understanding of spin transitions. The splitting of atomic energy levels due to spin interactions, called hyperfine splitting, is used to keep atomic clocks accurate to 15 decimal places. These clocks synchronize GPS satellites, enable secure communication networks, and contribute to scientific measurements that require extreme precision. Without a foundation in the behavior of spin, first revealed experimentally by Stern and Gerlach, these technologies would not exist. The experiment also influenced methods for controlling and preparing quantum states. Today, quantum control is a field that lets scientists manipulate single atoms, ions, and qubits with extraordinary accuracy. The fundamental idea that magnetic fields can separate, orient, and influence spin states came directly from Stern-Gerlach. Technologies like laser cooling, optical trapping, and state preparation in quantum experiments rely on this concept. The ability to select spin-up or spin-down states is central to creating clean initial states for quantum operations. In summary, the Stern-Gerlach experiment laid the foundational understanding of spin and quantization, concepts that have become central to technologies we now depend on. MRI machines use spin behavior to image the human body. Quantum computers use spin-based qubits to process information in ways classical computers cannot. Spintronics uses spin orientation to store and transmit data more efficiently. Atomic clocks use spin-dependent energy levels to measure time with unparalleled accuracy. All of this traces back to a simple experiment that revealed nature's hidden order. The profound impact of Stern-Gerlach is that it transformed an abstract idea, quantized spin, into something measurable and real. Once that door was opened, it allowed scientists and engineers to build technologies that harness the quantum world instead of merely observing it. The legacy of the experiment is not only scientific, but deeply technological, forming the backbone of innovations that continue to shape the future. One of the most fascinating aspects of the Stern-Gerlach experiment is that its enormous impact on physics came from a setup so simple that it could almost be mistaken for a classroom demonstration. At its core, the experiment used nothing more complicated than a heated oven, a beam of atoms, a magnetic field with a slight gradient, and a detection plate. There were no advanced electronics, no lasers, no high-energy accelerators, and no complex computing systems. Yet this simple arrangement accomplished something extraordinary. It exposed a fundamental quantum property of matter, reshaped scientific understanding, and laid the foundation for entire fields of modern physics and technology. It serves as a powerful reminder that groundbreaking discoveries do not always require extreme complexity. Sometimes they require only clear thinking, clever design, and an open mind to unexpected results. The simplicity of the experiment begins with its main components. Silver atoms were heated until they evaporated, forming a fine beam that passed through a tiny slit. This beam then entered a magnetic field that was deliberately made uneven. If classical physics were correct, the atoms, each acting like a tiny bar magnet, should have been deflected in various amounts depending on their orientation, creating a smooth smear of dots on the screen. This was the classical expectation. The beauty of the setup is that it relied on nothing but straightforward physical principles. Heat atoms, let them fly, expose them to a magnetic field, and observe where they land. It was designed not to confirm quantum theory, but simply to test whether atomic magnetic moments behaved in a classical, continuous way. What made the experiment extraordinary was how dramatically its results departed from expectations. Instead of forming a continuous spread, the atoms landed in two distinct spots. This simple observation, produced by a device with almost no moving parts, forced physics to confront a deep truth. The microscopic world does not follow classical rules. The splitting into two beams revealed something entirely new: the quantization of angular momentum, and later, the existence of electron spin. This was a discovery so fundamental that it reshaped the structure of atomic theory and influenced the development of quantum mechanics. The fact that such a monumental insight came from such a modest setup is part of its power. Most of the major breakthroughs in modern physics, relativity, particle physics, cosmology, are associated with elaborate machinery or complex mathematical theories. But the Stern-Gerlach experiment showed that big ideas can come from small tools. It proved that the right question, paired with careful measurement, can open doors that sophisticated technology alone cannot. In many ways, its simplicity was an advantage. It made the result undeniably clear. The sharp separation of atomic beams was not subtle or buried in noise. It was visible to the naked eye. That clarity meant that the scientific community could not easily dismiss it. Nature had spoken in a direct, unmistakable way. Another part of the experiment's profound impact lies in how its design captured the essence of quantum behavior without relying on theoretical assumptions. At the time, quantum mechanics had not yet taken shape. There were early hints: Planck's quantized energy, Bohr's discrete orbits, but no unified theory. The Stern-Gerlach experiment was not built to confirm an existing quantum model. It helped reveal the need for one. In other words, the experiment was not a test of a well-established prediction, but an exploration that uncovered a new phenomenon. This makes its simplicity even more remarkable. It provided the data before the theory existed, giving theorists a crucial clue that shaped their entire framework. Its impact was also amplified by how easy it was to understand. Many experiments in quantum physics require complex interpretation, but Stern-Gerlach gave a visual demonstration of quantization. 2 spots meant 2 allowed states. No complicated calculations were needed to appreciate the strangeness of the result. A student could look at the apparatus and understand the conclusion. This accessibility helped accelerate the acceptance of quantum ideas. The experiment became a persuasive teaching tool, an illustration of quantum concepts that could be explained in minutes. Such clarity is rare in advanced physics. The experiment also demonstrated how a simple design can uncover multiple layers of insight. At first, it showed quantized angular momentum. Later, it pointed to intrinsic spin. Even later, it revealed the role of measurement in collapsing quantum states. And eventually, it inspired technologies based on controlling spin. All of these emerged from the same basic setup. This progression shows how a single experiment can continue influencing science long after its original purpose has been fulfilled. The simplicity of the design allowed scientists to adapt, reinterpret, and reapply its logic across decades. Another reason the experiment's simple design had such profound impact is that it encouraged further exploration. Because it was easy to build, it inspired other laboratories to replicate and extend the experiment. Reproducibility is a core requirement of scientific progress, and the Stern-Gerlach apparatus provided a model that could be rebuilt without major cost or engineering burden. This allowed physicists everywhere to see the same results and build upon them. Simple experiments that can be widely reproduced tend to accelerate scientific revolutions, and Stern-Gerlach is a perfect example. The experiment also demonstrated a powerful truth about scientific inquiry. Creativity matters more than complexity. The brilliance of Stern and Gerlach was not in using advanced tools, but in asking the right question and designing an elegant test. Many of history's greatest experiments share this quality. Galileo dropping objects to test gravity, Young's double, slit experiment revealing the wave nature of light, and Millikan's oil drop experiment measuring electron charge. All of these used simple setups to uncover deep laws of nature. Stern-Gerlach proudly stands among them, showing that simplicity can be a gateway to understanding the most mysterious aspects of the universe. Its impact continues today not only through its scientific implications, but also through the way it inspires modern experimental physics. Even though today's technologies like atom interferometers, superconducting qubits, and MRI machines are far more advanced, their principles trace back to the simple observation made in Stern-Gerlach. Modern scientists still appreciate that simplicity can lead to clarity, and that clarity can lead to discovery. The experiment is a reminder that innovation often starts with a small idea executed well. Ultimately, the profound impact of the Stern-Gerlach experiment comes from the perfect balance of simplicity and depth. It did not rely on complexity to make its point. Instead, it used an uncomplicated setup to reveal a truth that overturned classical beliefs and opened the door to quantum thinking. Its legacy shows that sometimes the most transformative insights come not from massive machines or exotic theories, but from simple tools used in clever ways. The experiment taught physics that nature's greatest secrets can sometimes be revealed through the smallest and most elegant experiments. One of the most surprising and influential lessons that emerged from the Stern-Gerlach experiment is the idea that measurement does not merely reveal the state of a quantum system. It changes it. This concept is now a cornerstone of quantum mechanics, but in the early 20th century, it was a shocking departure from classical physics. Before this experiment, scientists assumed that measuring something simply uncovered a property that existed independently of observation. The Stern-Gerlach experiment challenged that assumption directly by showing that observing the spin of atoms forces them into specific states. It introduced an entirely new way of thinking. In the quantum world, measurement is an active process that shapes the outcome rather than a passive process that records it. The setup of the experiment was simple. Send atoms through an uneven magnetic field and watch how they split on a screen. According to classical physics, the atoms should have spread out in a continuous pattern based on their magnetic orientations. Instead, the atoms split cleanly into two separate spots. This was already strange, but an even deeper mystery emerged when physicists realized that the magnetic field was doing more than sorting the atoms. It was forcing them into one of two allowed states. The act of measurement through the magnetic field created the outcome. This was a radical idea because it meant the atoms did not have a fixed spin direction before they entered the magnet. Instead, the magnetic field caused something known today as state collapse. The atoms existed in a superposition, a combination of possible spin states until the experiment asked a question. The magnetic field served as the question. The atoms responded by collapsing into either the spin-up or spin-down state, and the detection screen recorded the answer. In this sense, the measurement process did not reveal a pre-existing fact. It created a definite result out of many possibilities. This was the first experimental glimpse of what would later become the measurement postulate of quantum mechanics. The idea that measurement affects quantum systems became one of the most debated and philosophically rich concepts in physics. It laid the foundation for the uncertainty principle, the observer effect, wave, function collapse, and the development of quantum probability. The Stern-Gerlach experiment provided the physical evidence that measurement outcomes are not simply about gathering information. They are about changing the system in the moment of observation. This broke with centuries of classical thinking, where objects always had definite positions, velocities, and properties, whether or not anyone was observing them. Another important contribution of the experiment was showing that the type of measurement determines the state that forms. If the magnetic field is set up to measure the spin along the vertical direction, then the atoms collapse into spin-up or spin-down along that axis. But if the experiment is rotated to measure the spin along a different axis, like horizontal, the same atoms will produce new outcomes, and the previously measured state will no longer determine the result. This means that measuring one property can erase information about another. The system reorganizes itself based on the measurement being performed. This insight later became essential to the formulation of quantum mechanics. The idea that different types of measurements disturb one another is at the heart of Heisenberg's uncertainty principle. Position and momentum cannot both be measured precisely because measuring one property disturbs the system enough to make the other uncertain. Spin behaves the same way. If you measure spin up or spin down in one direction, and then immediately measure spin in a perpendicular direction, the atom's spin will again collapse unpredictably. The Stern-Gerlach experiment made this behavior visible long before it was understood mathematically. The experiment also demonstrated that quantum measurement is inherently probabilistic. Even if you prepare many identical atoms and measure their spin with the exact same setup, you won't get predictable, uniform results. Instead, you get consistent probabilities. A certain percentage come out spin up, and the rest come out spin down. This introduced the idea that quantum mechanics does not deal with strict outcomes, but with probability distributions. The measurement doesn't tell you what will happen to any individual particle. It tells you how often each result occurs in a large group. This probabilistic nature of measurement influenced how physicists talked about quantum states. A quantum state became understood as a wave function that encodes probabilities, not certainties. When a measurement occurs, the wave function collapses, choosing one outcome based on those probabilities. The Stern-Gerlach experiment provided a clear physical demonstration of this long before the full theory was written down. Another major impact was that the experiment showed that measurement could be used to prepare quantum states. Before Stern-Gerlach, measurement was seen as a way to gather information, not a way to create specific states. But in the experiment, any atom that ended up in the upper spot was, by definition, in the spin-up state afterward. Any atom in the lower spot was in spin, down. In modern terms, the experiment produced purified spin states. This was the beginning of quantum state preparation, a vital concept for quantum computing, quantum communication, and quantum cryptography. In quantum technology today, preparing a qubit in a specific state, spin up, spin down, or a superposition, is the first step in performing quantum operations. The connection traces directly back to the logic of Stern-Gerlach. Use a measurement-like process to force a system into a definite quantum state. The experiment effectively demonstrated the first quantum filter, selecting particles based on their quantum properties. The experiment's influence can also be seen in the development of quantum entanglement and quantum information. When two particles interact and become entangled, measuring one immediately affects the other. This idea is built on the understanding that measurement changes quantum states. Without Stern-Gerlach providing the first empirical example of measurement-induced collapse, the later development of quantum entanglement theories might have been far slower. The experiment also inspired the philosophical debate between Einstein and Bohr. Einstein was uncomfortable with the idea that measurement could alter reality, or that particles did not have definite properties before being observed. Bohr, on the other hand, embraced the Stern-Gerlach results as evidence that quantum properties are defined through the act of measurement itself. This debate shaped much of modern physics and continues to influence how scientists interpret quantum mechanics today. Ultimately, the Stern-Gerlach experiment showed that the quantum world is not just hidden from ordinary senses. It behaves in a fundamentally different way from anything classical physics predicted. Measurement is not a simple act of observation. It is a dynamic interaction that shapes the outcome and defines the properties of quantum systems. This insight changed scientific thought, reshaped the foundations of physics, and paved the way for all modern quantum technologies. When we think about major discoveries in physics, we usually imagine brilliant equations, massive laboratories, or powerful machines. But one of the most important lessons from the Stern-Gerlach experiment is something much simpler and far more human. Great science begins with curiosity. Curiosity is the spark that pushes scientists to ask questions others ignore, to explore ideas that seem strange, and to test possibilities that look impossible. The Stern-Gerlach experiment is one of the best examples of this mindset, because it was born from simple wonder, not from advanced technology or from the goal of creating a specific invention. In the early 20th century, physics was at a turning point. Many scientists were uncomfortable with the new ideas of quantum theory. Classical physics seemed complete and predictable, but quantum ideas suggested something entirely new, that nature might behave in tiny, discontinuous steps instead of smooth motions. This was confusing and controversial, and most scientists preferred to ignore the strange parts rather than confront them. But Otto Stern and Walther Gerlach were different. They were curious enough to explore the mystery directly, even though no one was certain that the experiment would work. Curiosity is powerful because it gives scientists the courage to ask a question even when they don't know the answer, or even when the question seems strange. Stern and Gerlach wondered what would happen if you took a beam of atoms and passed it through a magnetic field. Classical physics predicted one thing, early quantum ideas predicted something different. Many scientists at that time would have said, "This is too uncertain," or "We don't have enough evidence to try this." But Stern and Gerlach wanted to know for themselves. That simple desire, to see what would happen, was the beginning of one of the most important experiments in modern physics. Their experiment looked almost ridiculously simple. A tiny furnace to heat silver, a slit to allow atoms to escape, and a magnet to bend their paths. Yet this basic setup became a doorway into an entirely new world. The splitting of the silver atom beam showed that electrons have a property we now call spin, something completely different from anything classical physics had imagined. Without their curiosity, this property might have remained unknown for much longer. This teaches something important. Scientific progress doesn't always come from big, expensive equipment or huge teams. Sometimes it comes from bold questions and simple tools used in creative ways. Stern and Gerlach did not have modern technology, advanced lasers, or digital tools. They relied on intuition, imagination, and the courage to explore the unknown. Their experiment proved that the universe still had surprises left, and that exploring those surprises could lead to discoveries far beyond what anyone expected. Curiosity also means being willing to challenge accepted ideas. At the time, many scientists believed everything in atoms could be explained by classical physics. The idea of quantum states was new and uncomfortable, but Stern and Gerlach refused to accept the comfortable answer. Instead, they asked, what if the quantum idea is right? What if atoms don't behave the way we predict? That question was bold and even risky. If the experiment had failed, some people might have laughed at them or said they were wasting time. Yet they were motivated not by the hope of fame, but by a desire to uncover the truth. Another lesson the experiment highlights is that exploration can lead to results far beyond what the original scientists imagined. Stern and Gerlach were not trying to build future technology or revolutionize medicine. They simply wanted to test a quantum idea. But their discovery of spin eventually became the foundation for magnetic resonance imaging (MRI), electron spin experiments, quantum computing, Spintronics, and many other technologies. This shows that curiosity-driven science can have massive, long-term impact, even when the scientists themselves didn't foresee it. In fact, many of the world's most important breakthroughs started with simple questions that didn't seem practical at the time. The Stern-Gerlach experiment reminds us that progress often depends on people exploring ideas without knowing where they will lead. Curiosity also requires patience and resilience. Stern and Gerlach didn't get perfect results immediately. They had to deal with technical problems, temperature issues, and weak signals. They had to adjust the magnetic field and refine the detection plate many times. A less curious or less determined team might have given up, but their excitement about the mystery kept them moving. This shows that curiosity is not just a spark of inspiration. It is also the energy that sustains long, difficult work. The experiment also inspired other scientists. After the splitting of the beam was observed, researchers all over the world began exploring spin, magnetic moments, quantum states, and measurement effects. This shows how curiosity can spread. One experiment can open the door for thousands of new questions and discoveries. Curiosity is contagious, and scientific progress often happens when one person's curiosity encourages others to ask new questions. Another powerful message from the Stern-Gerlach story is that science grows when people explore, even when they are not certain of success. In fact, Stern himself admitted he was not fully sure what they would find, but science thrives on that uncertainty. Exploring questions with unknown answers is how new knowledge is created. Curiosity allows scientists to step into the unknown, and that is exactly what Stern and Gerlach did. Finally, the experiment teaches that scientific progress is not only about results. It is about the spirit behind the work. The courage to explore, the excitement of discovery, and the joy of understanding something new are what push science forward. Stern and Gerlach didn't solve every mystery in physics, but they showed the world that curiosity is one of the most powerful forces in human progress. Their work is a reminder that the future of science relies not just on technology, but on imagination, exploration, and the willingness to follow questions wherever they lead. In this way, the Stern-Gerlach experiment stands as a tribute to scientific curiosity. It proves that even the simplest experiments, when driven by genuine wonder, can change our understanding of the universe. Their story encourages every young scientist to explore boldly, question deeply, and never stop being curious, because curiosity is the beginning of discovery.